Hey everyone, this is Trevor here. So today we will be learning this amazing data structure that is Fenwick Tree. So what is the use case? So let's understand the use case at first. So just in case if I say you that give me the sum between 0 and 3. So how can you give that? So you either loop from 0 to 3 to find the sum, or what you can do is you can store the prefix sum like 1, 4, 8, 9, 11. So if you're storing the prefix sum, you can simply go to 3 and say 9 is my sum from 0 to 3. So you can simply return it in O of 1 with a pre-computation of O of n. Again, if I ask you the sum between 2 and 4, so what you can do is you can say I will take the sum from 0 to 4 and then subtract the sum from 0 to 1, because 0 to 4 will take everything, and since I only require this thing, I can subtract this prefix. So that is why 0 to 4 sum, that is 11, and from 0 to 1 the sum is 4. So the sum that I get is 7. So that is eventually the answer. So if you are given such queries to find the sum between L and R, the complexity per query will be O of 1. Given a pre-computation of O of n is done before performing the queries. But what if I say you that there is one more operation, that is update. So if I give you update, then sum, then update, then sum. So then your prefix sum will not work, because if I say you to update this element by 6, so that means you're increasing this value by 2. So all the values on the left of the prefix sum has to be increased by 2, because now the prefix sum for here will become 10, this will become 11, this will become 13, because 2 has increased, right? So the sum, new sum from here to here is 10. New sum from here to here will be added by 2. So if a update is done, so you have to update your prefix operation, so that will take O of n again. Yeah, sum can be again done in O of 1, but update will be O of n. So imagine if you have multiple updates and multiple sum, so the worst case complexity for all the queries will be q into O of n, so which is nothing but O of q into n. So if q is 10 to the power 5 and n is also 10 to the power 5, so this will not scale. So this is where Fenwick tree comes in. A Fenwick tree allows you to do update operation in log n and to find the sum operation in log n. Yes, it does a bit of compromise in finding the sum operation, but then it is efficient, because just in case if you have a lot of update operations, then Fenwick tree is really helpful. So let's see how does the Fenwick tree look like. So before explaining the Fenwick tree, I like to give the reference to this wonderful tutorial written on the CF blog, as well as the forum of the top coder. So why am I giving the reference and why am I using the same examples? So just in case you get stuck, you can refer to those blogs too. Or if you're coming from that blog to over here, it will help you out. So let's take this array of size 16. So we know one thing, that any number can be represented in the powers of 2. If I write 11, that is nothing but 8 plus 2 plus 1. If I write 12, that is nothing but 8 plus 4. So we actually use the power of 2 concept to create the Fenwick tree. So let's understand how do we create the Fenwick tree. So we have a 0 node over here, that is the dummy node. So what we do is, at 1, whatever is the binary representation of 1, we write it down. So that is 1 itself. So what we do is, we turn off the rightmost bit. So when we are turning the rightmost bit off, what we get is 0. So the range for 1 and 1 is from 1 to 1. Because it was 0, so we do a plus 1, so we get 1. And whatever over here it is, so we write that. So we get the ranges 1 and 1. So for 2, what is the binary representation? The binary representation of 2 is 1, 0. So if we turn off the rightmost set bit, that is 1, we get 0, 0. So that means L will be 1. So we write 1, and what will be R? 2 itself. So 1, 2. So what will be for 4? 4's binary representation is 1, 0, 0. If I turn it off, that makes it 0. So it eventually is 1. So 1, 4. Now what is 5? If I write 5, it will be 1, 0, 1. So if I turn off the rightmost bit, it will give you 4. So L can be taken as 5. So this means 5, 5. So if we take 6, that is nothing but 1, 1, 0. So again we turn off the rightmost bit, so we get 4. So 6 is nothing but 5, 6. So if I write 7, 7 is 1, 1, 1. So let's turn off the rightmost bit. So what we get is 1, 1, 0. that is nothing but 6. So 6 plus 1 is 7. So L will be 7. So this refers to 7 comma 7. Again, what will be 8? 8 is nothing but 1 0 0. So if I turn off the rightmost bit, we'll get 0. So our L is 1. So if I write 8's binary representation, what will be that? 1 0 0 0. So if I turn it down, so we can write it as 0. So that means L will become 1. So this is nothing but 1 comma 8. So similarly, we can write down for all the others, and it will look something like this. So since we know how does the Fenwick tree looks like, so let's see how can we actually fill it up. So what does this representation means? So this representation means, so if I'm taking this 10th index, so this means it will store the sum between the 9th and the 10th index. So the sum over here that will be stored is between 9 and 10, that is 7. So this is what the representation means. Now what we will do is we will initialize everything with zeros. Think that every element in the array initially was 0. Now I suddenly say you to update the first index by 1, second index by 0, third index by 2, fourth index by 1. So this is basically an update operation that you are saying for every index. So if I ask you to update this first index, so what will that mean? So that will eventually update all the index in the Fenwick tree that gets updated by updating 1. So what does that mean? So I can say this will be affected, this will be affected, this will be affected, and this will be affected. Will there be anyone else who will be affected? Why will they be affected? Because this stores the sum between 1 and 1, and you have updated one index which is 1 and 1. Then you are updating 1 comma 2. Why? Because 1 is inside 1 comma 2. Then you're updating 1 comma 4 because it stores the sum between 1 and 4. So since you're updating 1, so the value at 1 4 has to be updated. Then this has to be also updated because this is storing the sum between 1 and 16, and you're updating 1. Why are you not updating 9 comma 9? Because this is storing the sum between 9 and 9, and 1 doesn't affect that. So how will you actually update this first index? So to do that, what you need to do is you gotta first go to this index 1 itself. So that is this in the Fenwick tree and update it by 1. So let's update. So once you've done that, you have to find what is the next index in the Fenwick tree that gets affected for the update of 1. So you know the next indexes can be 1 comma 2, 1 comma 4, or 1 comma 16. So you got to figure them out. So how do you figure them out? So the classical way to find the next is you find the 2's complement of 1. So write it in binary. So binary is 1. So you know the 2's complement of this will be actually 1. I'll not teach what is 2's complement now. After this, you have to do an AND with the original number. So the original number was 1 itself. So the binary of 1 is 1 and the 2's complement is 1. So you AND it. So you get 1. So once you've got this result after performing these 2 steps, you take this result and whatever was the original number, so that was 1. So you write it, and along with this, write this result, that is 1, and you add it. So when you're adding this, you'll get 0 and carry over 1. So you get 1 0. So you get the index as 2. So you know the next index that has to be updated is 2. So you go over there and add 1 to it. So let's add 1 to it. So once you've done this, so you've done for the second index. And now you want to know what is the next index. So how will you find that? So the next index to find that is again the same way. So what is the 2's complement of 2's binary? That is 1 0 itself. If you AND it with the original number, that will give you 1 0. So that is the result. Write 2 in the binary, that is 1 0. Do an addition to the original number. That gives you 0 0 1. So that gives you 8. So the next index that has to be updated is 8. So you go to 8, update it with 1. Let's find the next of 8. That is 16. So update it with 1. Now let's find the next of 16. Now that will be 32. So eventually that crosses your size of the array. So you do not do any further update operations. So I've updated it. Now let's try to update the second index. So if I'm trying to update the second index, the first thing is I'll go to the second index. So this is 1 comma 2. So I updated. So this gets added by 0. So this will stay 1 itself. So I know 2's next will be 8. Then it will be 16 because we just now did it. So since we're adding 0, everyone will stay as 1 itself. So let's move to the next, that is 3. So for 3, we go to the third index and we update it. So this gets updated by 2. That means you're adding 2 to it because that range is being updated by a value. So updating it by a value means you're adding that number to it. So what will be the next of 3? So write 3 in binary, that is 1 1. Write its 2's complement, that will be 0 1. Now let's AND it with the original number. So AND it. So 1 1 AND will be 1, 0 1 AND will be 0. So you get 0 1. So 3 can be written as 1 1. So 0, 1 is the value that is written from here. So you do add it. So 1 plus 1 will be 0, which carries over 1. So 1 plus 1 will again be 0, which carries over 1. So you get 1, 0, 0. So 3's next is 8, which is pretty obvious because 8 stores the sum between 1 and 8, and 3 lies in between 1 and 8. So 8's next will be 16. So you update 8 and 16. So you add 2 to it. So this becomes 3 and this becomes 3. So this is how, what you can do is you can update every index. Once you've done this, I can say this entire array has been updated. Now, what if someone comes and says that change A4 to 6? So previously A4 was 1. So the update that you're doing is a plus 5 because previously 1 was already updated because it had stored as 1. So the update that you're doing is a plus 5. So when you're updating it, so you're updating index and the value of add as 5. So you will eventually add 5. So starting from index, you move to its next, then to its next, then to its next, till it doesn't cross its boundary. And for every one, you're adding plus 5. So this is the way to do an update operation. And this will be nothing but a login operation. So you have understood how do you do an update operation. So you don't have to do this stuff again and again. So the shortcut to it is, if you can write this as I equal to I plus I and minus I. So this is eventually minus I means 2's complement, and then I and I means and with the original number, and add to the original number means I plus. So you get the next as I, right? So it's a simple equation that you need to do. You don't have to exclusively do all the 3 steps. You can write it in 1 step. So the update operation is clear to you. So once you have updated the entire Fenwick tree, the Fenwick tree will have values like 1, 1, 2, 4, 1, 4, 0, 12, 2, 7, 2, 11, 3, 4, 0, 29 stored. Now, if we check this out, let's say this one, 4. So 4 means the sum between 1 and 4. So if we do a sum between 1 and 4, so this is 4. So that is what it is stored. So this is how Fenwick tree stores. But then log and update has been done. But how does this help you to find the summation actually? So let's understand that too. So let's say I want to find the prefix sum from 0 to 12. So I know one thing, 0 to 12 can be written as 8 plus 4. So what I can do is I can go to 8 and say, hey dude, give me the sum between 1 and 8. So I'll easily get it, right? And for the next one, I can go to 9 and 12 because 8th index stores 1 to 8. And I also know that 12th index stores the sum between 9 and 12. So if I add them up, this will give me the range from 0 to 12 or from 1 to 12. Since I'm performing operation on 1 based indexing array, so it will be 1 to 12. So let's assume it is 1 to 12. You can easily get it. Now let's say I want to do for 14. So what will be 14? What will be nothing but 8 plus 4 plus 2. So 1 to 8, 9 to 12, and then 13 to 14. So that is what we have already stored in Fenwick tree. So since every number can be represented in powers of 2's, so we know what number of steps required will be log of n. So there is 2 ways to do it. Either you just break them down into powers of 2's, or the easier way that I'm going to explain. So the easier way that I'm going to explain is using some bit properties. So if I want to find this prefix sum from 1 to 13, what I do is I take the sum from 13. So I know 13 means 13 itself. And the next, whatever I want to take. So I will write 13 in binary. So let's write it. So 13 in binary can be written as this. So what I do is I turn off the rightmost bit. So once I've turned the rightmost bit, what I'll get is 1, 1. That is 12. So I go to the 12th index and take it. So I can see 12 means 9, 12. So I've taken it. And the next step, I write 12 binary, that is 1, 1, 0, 0. Again, I turn off the rightmost bit. So I get 1, 0, 0. That means 8. So I go to the 8 and take it. So I know 8 means 1, 8. So at the next step, I can turn off the rightmost bit. So I get something as 0, 0, 0. So anytime I've reached 0, I stop. So if you actually see, you have taken everything that ranges from 1 to 13. So this is how you can easily query. And since these are power of 2, the time taken to query will be log of n. So how do you turn off the rightmost bit? Because if you try to do it traversing the bits, again, it will take log of n. So the easier way to do it is you can find the 2's complement, then you add it with the original number. And once you have done that, you subtract it from the original number. So let's take this number 13. So 13's binary is 1101. So let's find the 2's complement. 2's complement will be nothing but this. Again, I'm not going to teach you how to find 2's complement. And then add it with the original number. So what we do is add it with the original number. So this is the original number. So let's add it up. So you get 1, 0, 0, 0. So you've eventually got this. And once you've got this, subtract it with the original number. So the original number was 1101. Let's subtract it. So 0, 0, 0, 1. So 1 minus 1, 0, 0 minus 0, 0, 1 minus 0, 1, 1 minus 0, 1. So you eventually got 12, which was where you were going, right? So we go to 12, then we find, then we again apply the similar steps to find the parent of 12. So the parent of 12 will be nothing but 8, and then the next parent will be 0. So we add 13, we add 12, we add 8 to our answer. So once you've done that, we can say that we have got the prefix sum from 1 to 13. So log n again. So this is how you can actually perform query and update operations in Fenwick trees. So let's quickly check out how the code look like for update and sum. So initially I declare a array that represents my Fenwick tree data structure, and then for the update operation I took index I that has to be updated, and then I took the value add that has to be updated in the Fenwick tree. So I know since the Fenwick tree is of size n, I can only go up to index n minus 1. So I'll go till n minus 1 index. So I add up the element at first, and then I try to find out the next element. So we did discuss how do you find the next element. Find the 2's complement, do an AND with the original number, and then add it up. So eventually at the next time you get the next element where you add up, and you keep on adding till you do not cross the boundary. So this is how the update operation looks like, and it works in log of n. So how does the sum operation looks? So for sum operation, you just need the index, because we have to find the prefix sum between 0 and I. So if you need the prefix sum between 0 and I, what you can do is, so you start on I and keep on moving to its parent till it is not 0. And in doing so, you keep on adding the values stored in the Fenwick tree. And you know you have to move to its parent. That is, you have to turn off its rightmost bit and move ahead. So how do you turn off its rightmost bit? So find the 2's complement, add it up, and then subtract it. So keep on doing till you do not reach 0. Once you have done that, you can simply return S. That will be the sum. So if it is said that you need the prefix sum between L and R, so it's very easy. You find the sum till R and then subtract the sum from 0 to L minus 1, and you can easily get it. So this is nothing but 2 into log n. So in the next video, I'll be talking about binary lifting on Fenwick trees. That is, how do you use binary search on Fenwick trees without actually using binary search.
So this is all about the video. Now let's talk about connecting. If you want to connect me over LinkedIn, this is my profile. If you want to join our Telegram channel, the link is in the description. If you have liked the video, press the like button. If you have disliked the video, press the dislike button. If you are new to my channel, do not forget to subscribe and to press the bell icon.